Our next speaker is Patrick from UC Berkeley, who will be presenting visual haystacks, answering hard questions about sets of images.
Hello everyone, I'm Patrick, and today I'm very happy to present our recent work about visual haystack, answering harder questions about sets of images. Sorry. It didn't respond. Okay, never mind. So I think in real world, there are a lot of visual problems requires long context reasoning. For example, like large-scale visual question answering regarding to a set of images. For example, like this one. As a parent, I usually deal with the problem about asking questions about my cats in a very large-scale photo albums. And also, there are a lot of important applications as well, like analyzing patterns in medical images, satellite images, or surveillance footage, etc. So, as a background, I think everybody has familiar with some large multimodal models after the ChatGPT era. So basically, it works like this one. We have an input image, and we pass that through the clip or other visual encoder, and then pass through a visual abstraction or alignment layer to transfer that to the text embedding layer, and then concat all of them and feed that into the LLM and do the next token prediction. So more recently, I think some models like GPT-4o or Gemini 1.5, what they do is like they make the context then larger to support or to accommodate more visual tokens in the models to scale up or support large-scale image QA. So the question remains, does taking more visual tokens really or actually leads to improve results in large-scale multi-image QA? So the answer is not necessarily, and we indeed need a benchmark to tell us or give us the number. So lead this to the needle in a haystack challenge. Maybe some of you have already heard of. So the idea is very simple. We have key information, we call it needle, and we insert that to a collection of data, we call it haystack, and test if the model can retrieve and answer the questions. So in the NLP domain, we have a very naive test, which is we insert a random information into a very long essays, and ask the model a very random questions about this information. So despite its simplicity, it can be a very great unit test to see if the model can actually reason long context text input. So we can apply the similar idea to the vision world. For example, like the Gemini team earlier this year, they proposed the first visual needle in haystack challenge by inserting some transcript to a single frame of a 2-hour video. And then they claim that, OK, Gemini 1.5 do pretty well on understanding a 2-hour video. So if we apply this challenge to all existing models, you will see something like this one. So in this artificial setup, which we only validate the model's ability on OCR-based or some outlier detection capabilities, you will always see some nearly perfect saturated results performance. And we didn't provide any signal or insights to see what direction the model can be further improved. So instead, we propose a new benchmark called visual haystack, which the problem can also be very easy. We have an image with the anchor object, and we insert that to a lot of images. We call it a haystack. And when the question is just like locate the which image contains the anchor objects and see if it contains the target objects. So by doing very little changes from the text space to the image space or from the artificial one to a realistic task, we see that existing models like GPT-4o and Gemini somewhat struggle or degrade the performance compared to what we see before, like nearly perfect results. So we can take a closer look at our data sets. We have a single needle track where there is only one needle image we cared about, or we have multi-needle tasks where we ask the questions like, do any or all of them contain a target object, which requires the model to do some cross-image reasoning, or we need to integrate information across the frame. And some other notes about our data sets, like all the images are from Coco. It should be very easy. And we have a lot of test case compared to a lot of cases just like, OK, we have a single test case that is not statistically meaningful. And the question are also very easy, like binary questions. So we thought this data set should be very easy, because we use Coco data sets, and the question is pretty easy. So there's no excuse the model should fail. So this leads us to do more exploration on existing models like GPT-4o, Gemini, 5.3, etc. So the first finding we found is that existing models actually are vulnerable to visual distractors. We first include two baselines here. First one is the detector oracle, which we use a perfect object detector, and we just test if it contains the anchor objects and the target objects as well, and use some basic logic to solve the problem. It serves as an upper bound. And another one is the captioning baseline, which we captions every image and then ask the LLM to answer that. It should also be very easy. So here's the result of all the existing large multimodal models. So as you can see, if we only have single image as an input, the left-hand side, which means that only image contains the anchor objects we're interested in, and the performance can be quite close to the oracle results as shown at the left-hand side there. So, but as the number of images increase, first of all, we can see that none of existing LLMs can take more than 100 images because of API rejection or out of memory for a 100 or out of context length, something like that. Another thing is that we can see a huge performance drops compared to the Oracle baselines. So that is something we probably can improve in the future. And the second finding is that we found that existing models are doing bad in cross-image reasoning. So recall our multi-needle data set. We always have 2 or 3 key images. We just feed that to the model, only 1, 2, or 3 images. And we can see that when the number of images grows from 1 to 2, the model performance degraded. But from 2 to 3, they kind of stabilize, or just stabilize. So the models can probably have some problems about integrating information across frame. And when we reintroduce the distracted image back, we can also see that the performance degrades further compared to the left-hand side, and also the single needle approach. So which indicates that there can be some room for improvement in how these models to do visual retrieval and reasoning. And the final finding is about the positional bias. So one thing about the single needle experiment is that we insert some key information in the haystack. But there are multiple possibilities, like we can insert that at the beginning, at the end, or somewhere in between. So we do that experiment. And here's what we found. So here's a very famous 2D heat map needle in a haystack. As you can probably see some trends, like the x-axis is the number of images. It is obvious that if we take more images, the performance drops. But now we are focusing on the vertical line. You can see, for example, like Gemini 1.5 Pro, the performance is somewhat higher if the number of images put, if the needle depth is closer to 0, which means we place that needle information at the beginning of the context. So we can take a closer look. For example, like this one, we plot it in the 1D. So it is Gemini model. From number of images from 1 to 100, it seems like they have higher performance if the key information is put at the beginning. So here's the GPT-4o. There's some loss in the middle effect also in the vision world. I think it's the first work that talking about loss in the middle in vision. So it is also some interesting finding we found. So after a lot of analysis, we just asked a question. Can we do better on this kind of large-scale multi-image QA? And we introduced a method called Mirage, which is a first, or probably pioneering, visual RAG framework that can take tens of thousands of images and can do retrieval and reason across multiple images, open source solution. So yeah, we'll elaborate it very quick later. So first of all, our model contains a visual compressor. It is because we all know that clip output probably contains 576 tokens, and it's very heavy. So we use a compressor to compress the number of tokens from 500 to 32. It can accommodate 18 times more images in the context length. The second stage would be a retriever, which the retriever will take the questions and the compressed visual information as input and output true or false as whether the images are correlated to our question or not. And if not, we just drop that. If true, we just pass that to the downstream or large language model during the inference. So this retriever is trained in line with the LLM during our training. So finally, because we need to have a data set to support this kind of large-scale image QA, so we just collect some existing multi-image QA as well as some augmented lava data sets to create a lot of distracted images for this purpose. To do the instruction fine-tuning, it leads to a 1.2 million training set. So after we train the model, we just revisit the visual haystack benchmark. Here is our single needle track. And this red line is our result. So first of all, it is the only method that can scale up to 10K images as input because we have a retriever, and the retriever can reject a lot of irrelevant images. And also, after 50 images, our performance can be constantly higher than GPT-4o and Gemini 1.5 Pro. So here's the multi-needle track. We also reduced it again. And as you can see here, the performance is not that good. So it indicates that there's still room for improvement in probably both the data side and the model design side. But we still need to say that our model is still on par of better than any existing open source solution so far. So we also do the experiments on conventional VQA tasks and show reasonable performance on all the benchmark, and especially the best performance on the multi-image QA, the red VQA benchmark. So here are some takeaways. First, we introduced a vision-centric and realistic long context benchmark for large multimodal models called Visual Haystack, which might be better than existing one that is artificial. And secondly, current models are prone to visual distractors, struggle with cross-image reasoning, and have some positional biases. Third, we present a new visual RAG model called Mirage that can take 10K images as input and mitigate some of the challenges because we have a retriever, so we probably don't have positional bias. And we also have a retriever, so we don't need to deal with the visual distractors that can be solved at the first place. So finally, as you can show that Visual Haystack and Mirage are not the endpoint, but a starting point that we need to further explore this this direction and see how we can improve in the future. So thanks for listening, and here's our project page. We have already open source. Thank you.
We have time for a few questions. Oh, there's one over here.
So what is your strategy to improve your Mirage model performance for multi-needle tracking? Do you have idea on improving it?
Yeah, that's a great question. So if we go back to the data set, we can see that, OK, there are only 3 open source data sets for multi-image QA. And all of them are very restricted, like this one are synthetic. And these 2 are only from Wikipedia, and it's only 12K data set. This one is only 20K. So I think the data side would be more important. Like, how can we integrate more diverse and better data to train the model?
Thanks.
On the Mirage work, if you could translate images to text, which you can do with these models, and did a RAG text only versus doing a image RAG, text to image RAG? Which one do you think would be working better?
I think at the end of the day, we still want to have a visual RAG because that can take more information. And as we transfer the information from, for example, from the image to the world, it probably lose some information. As you can see that here, where's that? We have the captioning baseline, which we caption that, and then we lose a lot of performance here.
But the encoders, the multimodal encoders, are not as well trained as an LLM in the multimodal LLM. So one would think that translating to text from an image would give you much more visual description that will help you answer more questions than if you just had a text-to-image multimodal model.
I think that is an interesting direction. We can see if the text base would be better or the visual base better. Thanks for the suggestion.
Do one more. This is the last question, by the way. Go ahead.
Hello, I have a question, a technical question about the compressor and the retriever. Can you go more?
Hold on.
Yes, this one. So I'm wondering, is compressor and retriever something what is pre-trained before you do everything with the large language model here, or this is a part of preparing this framework, the Mirage framework? You have to train compressor and retriever together in this to make Mirage active.
Yeah, that's a great question. So for the compressor, we actually, because the large multi-models usually contains the pre-training and fine-tuning, so we just pre-train the whole models with the compressor at the first, during the pre-training. So that is the compressor part. And the retriever, the same, we also pre-train that using some of the existing data. And then we do the instruction fine-tuning by unfroze all of things and tuning together.
All right, let's thank our speaker one more time.